Alright guys, next type of solid is our metallic solids, our metals in general. Just again, as a reminder, I know I keep putting this up here and it's probably driving you crazy, but I am doing it for a reason, I promise. We have our LDS, dipole-dipole, our hydrogen bonds, electrostatic, and then we have covalents, but we have what's considered a non-directional covalent, which I'm just going to abbreviate as ND, and then a directional covalent. And again, that's increasing strength, LDS being our weakest, directional covalent being our strongest. So in a metallic solid, we have what's called a non-directional covalent bond. What in the world does that mean? What that means is the electrons are delocalized. And those are delocalized throughout the whole structure. So think about like an electron cloud around one of these atoms, okay? But instead, what ends up happening is the electrons clouds almost end up fusing together. So this atom's electron cloud becomes fused with this atom's electron cloud, and so on and so forth. And it almost creates like this massive valence cloud, if you will, all the way around the structure, okay? And what that means is all of these electrons are being shared and spaced and throughout the whole structure, which is why we call it a non-directional covalent bond. The electrons aren't being shared between just two atoms, they're being shared within this whole structure. And we actually call this a sea of electrons, which you may or may not have heard in physical science. I know I learned the term in my physical science way back when, but over the last couple of years, every time I mention the term, it seems like you guys have never heard it before. So if you haven't, no big deal. If you have, good. Okay, but it's called a sea of electron. And again, the reason being is it's almost like the electron cloud fills all the space between all the atoms, and it becomes one massive cloud around the structure in itself. And the electrons are kind of like free-flowing all throughout, and I know it's kind of messy, but that's kind of the idea. And they're just kind of moving and flowing, and again, we are referring to valence electrons. Again, you can kind of see this picture here where the electrons are free-flowing. They're not moving in any particular direction, they're not between any particular atoms, they're just everywhere between all the atoms, which is why we call it either delocalized or non-directional covalent bond. Again, these are weaker than our directional covalent bond, which what that means is, again, in terms of strength, our metals are going to have kind of an in-between melting point, boiling point. They're going to be higher than our ionics, but going to be lower than our covalent network solids, which we'll see in just a minute. And of course, our moleculars are our weakest, way up here. Okay. Some things we need to know about metals, and we're going to talk about alloys just a little bit here too. Whoops, sorry about that. They are this. Sorry, I'm trying to get my words going here. The way they are packed together is called a closet packing system. And it may be a little bit hard to kind of see here, but what I want you to imagine is take like a little box and layer the box with tennis balls across the bottom of that box. Okay, now put another layer of tennis balls onto that first layer. Where are those tennis balls going to fit? Well, they're going to actually go on top of the space. And again, I know it's kind of hard to see. Let me see if I can do a little bit better. If I have these tennis balls here, this space right here is where the next layer is going to fit on top of. Okay, and that's kind of what's going on here. It's almost like they're kind of fitting in the crevices that the first layer creates. And that's going to be so on and so on. So just kind of imagine taking a bunch of tennis balls and layering them on top of each other. Okay, and that's what the closet packing system is. And that's going to play a role when we look at alloys in just a minute because of how those holes interact with the different types of molecules as well as what the atoms will do with themselves. So again, these guys are going to have higher melting points and boiling points. Again, this is a generic term, high, low, etc. It's in the grand scheme of things. Again, their melting points and boiling points will be, in most cases, higher than an ionic solid and much higher than that of a covalent or a molecular solid, excuse me. Again, there are exceptions. For example, zinc's got a fairly low melting point, and that all kind of just depends on the structure and how everything flows together. So there's always exceptions, but again, in the grand scheme of things, most metals have significantly higher melting points and boiling points than that of our ionic compounds. And again, there are some ionic compounds that have higher, some metals that have lower. That just happens, okay? These guys are good conductors, okay? So again, what is a conductor? A conductor is having the ability to have electrons flow or have charges flow. Well, think about this. Remember, this cloud is one massive cloud of valence electrons, meaning the electrons are already free-flowing. What that means is if I create a positive end on one side and a negative end on the other side, the electrons are now going to be pushed, if you will, from this negative charge, and they're going to flow towards this positive charge, and therefore creating electricity. Okay, metals are very, very good conductors. And of course, our best conductor, which I believe we've talked about, is gold. And we don't use gold in our houses or in our electronics, really. Instead, we use copper for basically cost's sake. But if you have a HDMI TV, what I want you to do is look at your HDMI cable. If it's a really high-end cable, what you notice is that the plug is actually coated in gold. Why? Well, the HDMI cable needs to be able to carry a good signal for a good, strong picture to be able to be transferred. So you use the best conductor you can. Gold in this case, okay? And again, that just comes down to that closet packing system and the free flowing of electrons. Again, most metals have high densities, and again, of course, there are exceptions to this. There are very low dense metals and there are very high density metals, but this is a grand scheme, are generic, are just maybe an overall trend, if you will. And of course, these guys are malleable and ductile. What does that mean? It means they're able to be hammered into sheet, flattened, rolled, etc. Why? Well, what I want you to think about is these tennis balls right here. Remember, we talked about how they're packed together. We'll take the box out of the equation and just say you have a bunch of tennis balls stacked on top of each other in layers. Well, if you take a hammer and hit the top tennis ball, what's going to happen? They're going to spread out, okay, and they're going to kind of collapse down and move freely. Sorry about that. That ability to move freely and space out is that malleability and ductileness, and none of the other structures are really able to do that because they're not packed like this. Their lattice structures are not set up like this, nor do they have this free-ranging cloud that kind of just holds everything together but allows for flow and flexibility, if you will. Okay, so that's metals. Now let's talk about alloys. Alloys, if we remember back from honors chemistry, is where we have two metals or a metal and something else all mixed together, and they're carrying on metallic properties, or keeping the metallic properties. And sometimes the point of an alloy is, actually there's multiple points of alloys. Alloys are created for color. Some cases, like rose gold, for example, is predominantly a color, but also a strength, because gold is very, very soft. Yellow gold is not pure gold. The gold we use in terms of jewelry is not pure gold. It is an alloy. Again, reason being is gold is very, very soft. So sometimes we're trying to make it harder. Sometimes we will make material more flexible. For example, steel. If you are building a giant skyscraper in California, okay, you want to use steel for your structure, but do you want that steel to be rigid? No, think about it. If you have an earthquake and you have the building twisting a little bit, if you have a really rigid metal holding that structure up, it's going to cause it to crack or split, which could then cause the integrity, structural integrity of the structure. So alloys are made for multiple different reasons. A lot of times they are strengthening properties, whether it's making them harder, making them more flexible, making them have higher melting points, making them more magnetic, also could be something that they're trying to do. So there's a bunch of different reasons behind alloys, and what you use for that alloy is what allows you to come up with those properties. Okay, so there are two different types of alloys as well that we need to talk about: substitutional and interstitial. So substitutional is exactly what it sounds like. So think about to our tennis ball analogy, our closet packing system, closet packing system. Okay, we have our tennis balls, they're all kind of stacked on top of each other, etc., etc. Let's say I go in and I remove one of these tennis balls and I replace it with a baseball. Okay, there is a little bit of a difference between a baseball and a tennis ball in terms of size, but for the most part, they're very, very similar. This is kind of very similar to what we have with a substitutional alloy. So let's say all of these atoms are iron. Okay, and what I'm going to do is I'm going to go in and remove one of the iron atoms, and I'm going to replace it with, let's say, silver. Okay. Yes, I know they're on two different periods in the periodic table, but if you remember looking at your atomic sizes in that D block section, they're all still very similar, even though they are different periods, and you can look up your atomic radius and kind of see what I'm talking about there as well. They're very, very similar in sizes, and therefore what we do is we're just replacing one of the atoms with the silver atoms, one of the iron atoms with a silver atom. Okay, also could be the same thing, like let's say I take iron and germanium. Again, very, very similar size, so they can just be replaced. So substitutional is just taking two things very similar in sizes, okay, and I'm going to put that over here, and just replacing it. Versus is an interstitial alloy. Okay, so remember again, we have these balls that are stacked on top of each other. Okay, well, think about it. With the tennis balls stacked on top of each other, is it going to be a completely compact structure or design, or are there going to be holes in it? Well, there's going to be holes in it, so notice kind of these holes right here. An interstitial alloy is when we take a small atom in comparison to the atoms that are in the metal already, and we fill in those holes. So kind of think about it like taking marbles and pouring it into the tennis balls. Okay, the marbles are going to go through and fill in those spaces. Okay, or maybe taking golf balls and kind of putting it in there. Again, it's going to kind of fill in the spaces, so golf balls are a lot bigger. That is what an interstitial alloy is. So it's kind of filling in these spaces that are left from the atoms themselves. Okay, and this is only going to happen if you have a significantly smaller atom. So this is very common, like with our iron carbide. Carbon is significantly smaller than iron, so it ends up filling in these spaces. So that's kind of the difference between these and being able to recognize those differences. Okay, so that's metals and alloys. Moving on to our last type of solid we're going to talk about, which is a network solid. And don't get confused by the molecular term being in here. I typically will only call them network solids, but they are atomic or molecular network solids. These are where you have your lattice points, whether they're atoms or compounds. So in a lot of cases, they are atoms. There are some that are compounds. For example, quartz, which is SiO2, is a compound. So your lattice points, or your vertexes, are either atoms or compounds, and they're being held together by actual legitimate covalent bonds, directional covalent bonds, meaning the electrons are being shared between these atoms. Okay, some of the common ones we need to just know and recognize are diamond, graphite, and quartz. Those are the common ones used by college boards, so you need to recognize those in particular. These are extraordinarily strong structures. So again, these aren't intermolecular forces. These aren't even non-directional covalent bonds. These are legitimate covalent bonds that these atoms are sharing electrons between each other, and therefore they are very, very strong forces of attraction holding them together, which makes these guys very, very strong in terms of melting point, boiling point. These guys typically have our highest melting points and boiling points, and they are the highest ones. So think diamond. It's got a very, very high melting point, boiling point. These guys are typically poor conductors. Why? Again, there's no freedom for the electrons to flow. They're being held very specifically. So these actually have electrons in them. These bonds do. Versus our intermolecular forces don't. The directional covalent bonds do have the electrons in them, but they're being held very tightly between these two atoms, so they're not able to flow or move, therefore they can't conduct electricity. The other thing is here is these guys are not going to be soluble in water in any way, shape, or form. Okay, again, because they're being held together by covalent bonds, they can't dissociate, they can't just separate. So if I take my diamond from my wedding band and drop it in water, it's not just going to magically dissolve. If it did, we wouldn't be using diamonds for jewelry, would we? Okay. They can vary in densities, but they are commonly very high in densities. And they can vary in conductivity, but typically they are very poor conductors, and they are typically considered very hard. Again, these are general rules. They do vary, so keep that in mind. Okay, so that's kind of it for these. We're not done with them. I want to spend just a little bit more time talking about solids and kind of going through and making sure we understand some of the properties and are able to identify them. But that is it for this video. So again, we've talked about our 4 types of solids, as well as alloys, which fit under the metal category, and hopefully we can solidify and make sure we understand the concepts in the next video. Thanks, guys.